Hey everyone, so I left with the last video talking about how we had two different ways to add vectors together in order to find a resultant. And I discussed the graphical method, which, as I said, most of the time it's not super useful. I mean, you do need to know how to draw vectors in general and that whole idea and how to use them. But for the most part, it's not really going to be your go-to unless you have very complex, numerous vectors that you're combining. More often than not, you're going to end up using the second method where we actually just use math and algebra. Well, I shouldn't say algebra, more trig and geometry and things like that. So this is how we'd add vectors mathematically. Now, once again, everything I'm going to do, I'm explaining so that you can use the same process for whatever complicated problems you have. Again, you might see problems that are much simpler, that have two vectors that are perpendicular, or vectors that only go left and right, and you may not feel like you need to go this hard, but I'm just putting into words kind of what you're essentially doing. And this is all actually based off of what I mentioned in the last video where I said if we multiply a vector by a negative number, by a negative scalar, it flips the direction. So what we're going to actually define is one direction to be positive and another direction to be negative. And from here, we can combine them simpler until we get one final vector. Now, the first step is to group like directions. What I mean by this is that if you have directions that are going in different dimensions, let's say, so north and south, east and west, left and right, up and down, those are different dimensions. North and south are parallel to each other, east and west are parallel to each other, but north and east are not in the same dimension. So we want to group them because when we use this addition method, we can only do it for vectors that are parallel or anti-parallel within the same dimension. So north and south being within that, if you want to think about it like a graph, on the y-axis of the graph, we can add any vector in their y parts, but we can't just add an x to it. That's not how that works. East and west, again, they're parallel, so we can add them up. So this is what I mean by group-like directions, because everything I talk about from here on out is just dealing with one of these groups, or I guess you could use both groups at the same time, but you won't be able to combine them until later. The next step is to define positive and negative. So we need to know what direction we're going to say are the positive vectors, which one are the negative. Now there is a convention that we use, and that's pretty much that north, east, right, and up are positive vectors, south, west, left, and down are negative vectors. If you think about this, this makes sense because it relates back to what I said with the graphs. That you have an x-axis and a y-axis. If you think about the graph, going right and up along the coordinates in that graph is going positive. Going down or going left is negative. So that's kind of where the convention is. The one thing to note is that you don't need to stick with this. If your setup is generally going to be going down, you can actually define down as positive and up as negative. You just need to make sure that you're being consistent. You'll see later on when I end up doing this, going against the convention, because as long as I'm consistent, that's all that matters. The third step is add up all the numbers. Again, we grouped them in step one, so we're maintaining that group, and then we add up those numbers. The resulting sign ends up telling us our final direction. There is a fourth step for when you have multiple groups together, and we'll see what happens there because what we're going to end up having are two perpendicular vectors. How do we get that resultant? So first, we're just sticking with the 1D. We'll use the same example that we did before in the graphing where we go 5 meters east, 10 meters west, 3 meters east. My displacement, step one, I can skip because they're all like directions. They're all going east and west. Step two, these distances or displacements become plus 5 meters, minus 10 meters, plus 3 meters based off of the convention. Step three, I add them up, maintaining that negative sign. So 5 meters minus 10 meters plus 3 gets me negative 2 meters. So putting this all together, we end up getting that it's 2 meters west because of the negative sign matching with my convention that I did before. All right. So that's pretty much what the addition method is. Like I said, most of you probably were able to see some of the 1D questions and do this, naturally without doing this all these steps. Like I said, I'm just putting it into words. Now, like I said, this is kind of related to what would you would do when you end up with the after you have your two groups, you add them. What do you do when you have your final north direction and your final east direction? This is what ends up happening. So let's say you have the scenario where you go 5 meters east, 10 meters north, 3 meters east. So step one, where we have to combine like directions, the 5 meters and the 3 meters, those are in the same dimension. So I'm going to group them together, and the 10 meters is in its own separate group. Doing the same thing, west being negative, east being positive, north being positive, south being negative. The 5 and the 3, which I grouped, I can add them up. Both of these are positive numbers, and I get them. In that dimension, the resultant is 8 meters east. The 10 meters there was no other vector that went with that, so that stays as is. And now we end up getting these two final vectors. So I have an 8 meters east and a 10 meters north. My resultant will end up being the arrow that goes from one end to the other end, or based off the shape, the hypotenuse of the triangle that I make. Now, the 8 and the 10 actually have a special name. So when you take a vector, and if you can simplify all the vectors so that until you get a complete horizontal and a complete vertical, we actually call those components. I'm going to mention that later on when we get to the second unit on projectile motion, since it plays a little bit more of a role there. Uh, but that's what these two are called. These are called the components of the resultant because they're the basic how far total east or horizontal and how far total vertical do you have to go to get that same resultant. From here, since I have these two sides and I'm looking for this hypotenuse side, I can go and pull out Pythagorean Theorem, a squared plus b squared equals c squared, plug the numbers in, and I get that this is 12.8 meters. Another thing I mentioned before that sometimes you might be tasked with finding the angle. In the graphing method, you could just pull out a protractor and measure it. Well, how are we going to find the angle without the diagrams, without a protractor? We have to pull out SOHCAHTOA. Doesn't matter which form of SOHCAHTOA I'd use. In here, I'm going to use tan. So tangent of this angle is going to be opposite over adjacent. So 10 over 8. 10 over 8 is 1.25. To solve for the angle theta, I have to do the inverse tan. So I have to move the tangent over, do inverse tan of that 1.25. And if my calculator is in degree mode, you'll end up getting 51.34 degrees. All right, so here we have our magnitude and the angle direction with respect to the horizontal. So that's how you use the addition method when you have two dimensions. Well, in the regions, that's pretty much as complicated as it gets. If you might see this type of question on the regions, but it would strictly be focused on the graphing aspect, not necessarily the mathematical aspect. But in the AP, there's a good chance that you might have a scenario like this where you have to calculate it and you don't have the room or the materials to graph it. So how do we do this? Well, there's actually two different ways to handle this. Each one, again, brings its own benefits when it comes to doing it on the test. The first is to do law of cosines. So you could do law of cosines or a variation law of sines, but strictly law of cosines. This works for obtuse or I should say non-right triangles to find one of the sides, in particular the hypotenuse side or the side opposite whatever angle we have. The thing though here is that the reference tables that you have, regardless of which test you're taking, wouldn't normally have law of cosines. So you have to memorize this, which is where the downside comes from. One thing that I do though is I actually just recall that it looks very similar to Pythagorean theorem, but with an added section. I can actually think about what that added section is based off of just knowing how it kind of gets set up and how it comes to be. But this is what you'd have to do. You'd have to memorize this equation. So C in this case will be our hypotenuse. A is going to be A and B are the two sides, and then cosine C, the angle that they're referring to, is this angle. The main thing here is that when you're doing law of cosines, you have to make sure that you have either the side or the angle that are opposite each other. So if you want to use law of cosines to find this angle, you need to have the side that's opposite it, and vice versa. From here, right now we don't have this angle, so we have to use geometry. We have a flat line, and then we have a line bisecting it, or not bisecting it, but crossing it. So we know that this entire angle should add up to 180. If this angle is 53, then this should be 127 degrees. So from here, I now have enough information to plug my numbers in. 8 meters squared, 5 meters squared, all this stuff, cosine of 127 degrees. And I should end up getting 11.7 meters. So that's what you could do for law of cosines. What I was mentioning with law of sines, if you recall, law of sines was essentially, actually, I want to rewrite this a little differently. A sine of A equals B sine of B equals C sine of C. So you could use this as well. The only thing here is that it requires you to have two angles and a side, or two sides and an angle. Essentially, you need two of one thing and then one of another. So in this case, within this triangle, I have this angle. I don't have this side, and I don't know what this angle is. I don't know what this angle is. And these are opposite the sides, so we actually don't have nearly enough information to use law of sines. But if they told me that this was 30 degrees, then I would have enough information. I'd have angle A and side A, and then I'd have the other angle and the hypotenuse side. Now, the second method, it can be a little bit on the easier side, again, depending on the setup. But essentially what you would do is you would break this this vector, the 5 meters, into its components. Because instead of using law of cosines, we can actually use Pythagorean theorem. But in order to use Pythagorean theorem, what we need is a right triangle. So we need to know exactly how tall this the resultant vector is, and exactly how long or wide it is. So if we can figure out this component, since we already know the 8, the height's coming from the vertical aspect of the 5 meters, and that extra distance is coming from, the horizontal aspect. So breaking this into its components to figure out how much of it is going in the x direction, how much it's going in the y direction using SOHCAHTOA will help us determine this right triangle and allow us to use Pythagorean theorem. Because remember, the whole thing is we can only really add up x and y, so we have to break up the 5 meters into x and y. The reason I say that this is something that you're very likely to do, and probably something that's very common, is because this is something that we'll end up doing a lot in the fourth section, where we're going to break things that are up at angles into components in order to add horizontal and vertical together. So this is something that you're probably going to experience a lot. though in my opinion you probably wouldn't do it with anything more than one angled vector. If you had three angled vectors, like maybe there was a third one going off in this direction, this method would be way too complicated. All right, so clearing this, so if we break up this 5 meters, we can use SOHCAHTOA to figure out that it's 4 meters tall and 3 meters to the side. Recall that with SOHCAHTOA, sine is equal to opposite over adjacent, opposite over hypotenuse. This angle is the angle that we're referring to. So the opposite is the 4 and the hypotenuse is the 5. So this becomes sine 53 is 4 over 5. Oh, sorry. We're looking for this, x over 5. Solve this for x and we get 4. We could do cosine to figure out what this side is, or now that we have two of the sides and we're looking for the last one, Pythagorean Theorem. So essentially we have to end up doing SOHCAHTOA at least once in order to find the components. But now that we have this, we know what the right triangle is for our main resultant. We know that it's horizontally 11 meters, it's vertically 4 meters. We could do Pythagorean theorem straight up, get the same number of 11.7, and then finding the angle is even easier because now we could just do SOHCAHTOA again to figure out that it's about 20 degrees. And that's pretty much it for how you would add them. So try looking at this question. Pause the video, work itself, and move over in a second. Now the key thing here is that you're not able to just connect these two sides to make your triangle. Because if you notice the way that this diagram is drawn compared to all the other ones, this one's not drawn tip to tail. We have two arrows where their tips or their tails are in a different direction and their tips are all going in the same point. So you have to redraw this before we can actually start solving this. Typically, you want to redraw it so that you have one arrow, and then right where the tip of one arrow ends, the next arrow begins. Make that treasure map. Another thing you can do is you can draw a parallelogram. So I can redraw this 24 meters up top, again parallel to what I have here, trying to maintain the same length. I can redraw this 18 meters over onto the other side. So now we have a parallelogram. The two opposite sides are equal to each other. And I know that these two angles are opposite each other are equal. Also, I know that these two angles should be equal, so I can use the whole geometry that all the angles should add up to 360 to find that these two angles are going to be both 130. From here, to draw my resultant, it's going to go, the resultant's going to start at where all the arrows are starting and end where all the arrows are ending. So my resultant looks like this, going from one corner to the other. So as you can see, completely different than if you just thought that connecting one side to the other side and making a triangle here without drawing the parallelogram was good enough. You can already tell that the length is significantly different as well as the direction. So from here, we can use law of cosines. Since I'm looking for this side, I'm going to make sure that the angle I'm using is this, that's opposite it. So I plug in my numbers, 18 and 24 in for A and B, the 130 degrees in for the angle, cosine C, and I get 38.15 meters. And that's pretty much it. In fact, you should have remembered learning this law of cosine equation with at the same time you learned about parallelograms. In fact, that's how I remember it, is that parallelograms use the law of cosines because parallelograms always have non-right angle triangles, essentially. So they always have these obtuse, acute angles that we can use law of cosines to find the diagonal very easily. So to me, whenever I think of the law of cosines, I think parallelogram and vice versa. So maybe that might help you remember. Even if you had a case where the two arrows were perpendicular, like this, even if it's drawn properly, I probably would still recommend um, drawing a parallelogram, mapping this arrow up here, mapping this one over here, and doing the same thing. Okay, the two arrows start here, they end over here. The main reason I say that you should probably do this regardless of how it's drawn is because it's very easy to overlook the way the arrows are drawn. If you get into the habit of just doing it every single time, regardless of whether the arrows are drawn tip to tail or not, then you'll never get tripped up because you're always doing it. You'll always do it out of habit and then go, okay, it starts here, ends here, boom. In addition, you'll always know how to do it when you need it. If you only do it for the arrows that aren't tip to tail already, you're not going to see too many examples of that. In fact, you probably would see more where they are tip to tail. And that means that you're going to be more likely to just go, oh, okay, I have to connect this side to this side, do that 10, 20 times, and then the one time where the arrows are drawn this way, you'll still naturally just say, okay, it's going this way. So that's why I recommend draw the parallelogram regardless how they're drawn, and do, you know, all the arrows start at one point, all the arrows end at another point. And that's pretty much it. That's it for this whole vector addition. Like I said, we're going to be constantly referring back to this. We'll do a few examples of this later on, and you'll see a little bit more of how this kind of works in this class. If you have any other questions, feel free to let me know. Otherwise, good luck and have a great day.